Hi everyone. In this video we're going to talk about queues. Now, like a stack, a queue is a specialized linear data structure. So it's a collection where we can put stuff in the queue. We have the queue hold on to different objects for us, and there is a sense of order. There's a first object, a second object, a third object, and so on. But what makes a queue special is we always add elements to the end of the list and remove elements from the head of the list. So like a stack is specialized in that we're always putting data on and off the same end, a queue we're putting data on and off opposite ends. So we call this FIFO. The first element in the queue becomes the first element out of the queue. And so the queue is just sort of the British way of saying waiting in line. So a queue would model something like the checkout line in a grocery store where you get in line, wait your turn, waiting in line for a roller coaster, cars at a stoplight, an assembly line. We use queues all the time. So here's a conceptual model of that, right? You got the front of the queue and the rear of the queue. Elements go on the end, they come out the front. Again, kind of hard to dig in any more than that. It's something we kind of have implicitly done for years. So just for a little bit of terminology, NQ means to get in line or queue up, and so that's adding an element to the end of the queue. When we take something off the front, we call that dequeuing, or getting out of line, being serviced from the head of the line, however you want to look at that. If we have this data structure, we may want to see who's waiting at the head of the line without actually pulling that person out of line yet. We want to see if perhaps the queue is full or empty, how many people are in line, and then everything has a toString. Okay, the obvious implementation of a queue is with a linked list. Because with a linked list, when we have both head and tail pointers, or as they're called here, front and rear, then we can both insert and remove elements in constant time. Right, so if you'll think back to when we did the linked list with these front and rear pointers, we can add elements to the end of the list in constant time. We can add elements to the front of the list in constant time, and we can also remove elements from both sides. So in this case, whether we're adding from the front and removing from the rear, or removing from the rear and adding from the front, that's kind of arbitrary. So we look at this queue here, we have A, B, C, D, and we've decided that the head of the list will be our front. So A is the first person in line, the D was the last person to get in line. So if we go to add another person in line, that's an add at tail, and we can see here that object E is now in line at the end. And when it comes time to servicing the next object in line, we can see that A has been removed from the front of the list. Now, implementing a queue with an array is a little trickier, at least doing it efficiently. So the obvious thing to do, as at least a starting attempt, would be to say, okay, 0 is the front of the list, so A gets put on the list first, and then B, and then C, and then D, and we just fill the array up. The problem is that when we want to take A off the list, we want to be able to do that in constant time. And with the array set up like this, it would be a big O of n operation to pull A off the list. We don't want to do that. So let's see if we can come up with a way of using an array and still getting that constant time NQ and DQ as with a linked list. The trick is to treat the array as if it were circular, which means instead of picturing the array as just a line, picture the array this way as if it wrapped around onto itself. Maybe thinking of a clock might be helpful. So that we'll put in elements 0, 1, 2, 3, and so on. So we'll work our way around the clock. But the next element after the last one, it just wraps back around to the first one. Here we have another diagram of a circular array, and it has 4 elements in it. You can see, for example, that the front of the queue has shifted clockwise to spot 3. There's 4 elements in it, and the end of the queue is listed here at 7. And what that means is that the next item to be put in the queue will be put in slot 7. Notice that this system will move the elements in the queue clockwise around this conceptually circular array. As we add new elements into the queue, they get put at the end of the queue, so it will, let's say it's E, F, G, H. As we do that, the end of the queue moves clockwise around, and then as we take elements off the head of the queue, then the head of the queue also moves around clockwise. So as you add and remove elements over time, all of the elements will have shifted clockwise, and of course at some point they will straddle that boundary where we conceptually wrap around from the end of the array back to the beginning of the array. Let's take a different view of that. So let's take that circular array and unwind it and look at it in a more linear fashion like we're used to with an array. So here, this first diagram at the top shows an array-based queue at the very beginning. So at the very beginning, the array is empty, and we put in 8 elements here, A through H, and we can see that they just end up in the first 8 slots in the array. Now, if we then take some elements off from the head of the queue, so remember first in, first out, so A and B were the first 2 in, they're the first 2 out. As we take things out, the other elements don't actually move. This would be different from a standard like line at the grocery store where you're not moving. It's almost like the cashier is coming toward you. So that front has moved along as we've taken stuff off. And then if we add more items to the queue, like I, J, and K, that's the third diagram at the bottom here, then they get added on to the end of the array, and when we reach the end of the array, it wraps around to the beginning. So that's another view of that queue having slid clockwise around and now straddling the boundary like we saw a minute ago. And the trick to making this whole thing work is just using the mod operator. So we can add things to the front and the rear as usual. We just add 1 every time we move around. But the quick and easy way to make that value wrap back around to 0 is to take the mod of the queue length. Now I will mention, if this wasn't obvious before, if you have a fixed length array, then you have obviously a maximum queue length. So if you create an array of size 100, you can't have more than 100 people in the queue at a time. Otherwise, the back end crashes into the front end and you start to get bugs. So if you have an application where you have a known maximum for the queue size, the array is a nice efficient way to get that done. If you don't know how big the queue might get, then of course you need a linked list or an array list or something that's potentially more flexible. Okay, so that's all I have on queues. This video is intended to be a supplement to the chapter in the textbook, so make sure you do read that if you haven't already. But even with the supplementary text, there isn't a whole lot to add about queues. Once you've already looked at linked lists and array lists, it's just sort of a special use of that. Many of the ideas of a stack transfer as well. Really the only thing we're doing differently is changing what ends we're putting things on and taking things off. And so, as I said, anytime you've got a situation where you've got objects waiting in line for something, waiting in line for some action, then you're looking at potentially using a queue data structure. As always, let me know if you have any questions, if there's any more details you'd like or something you'd like me to explain a little more clearly, and I will see you all soon.